later on. There's one more example, and before doing that, because we will use energy methods, I will repeat some of the basics of energy methods. Some of you, if not most of you, have seen them in the second year, because I use pretty much the same slides on this part. So consider it a reminder. The governing partial differential equation is almost impossible to be solved in any kind of a general case. The cases we saw here were interesting because they actually relate to some useful problems and you can solve them exactly, and there are very few cases like this. So you need other methods that allow you to solve these equations approximately and reasonably accurately. And that's where you say I can use my finite element model, and you are very welcome, if not good for you doing it. But if you're trying to get a feel of what the solution should be to compare, let's say, your finite element results, then you would need some solution like this. Or if you're trying to do an optimization problem where you need to run a relatively fast solution many times, you can't afford to keep running your finite element model every time. So, plus, I guess the main thing is you solve with your finite elements and you go show it to your supervisor and they tell you it's wrong and they don't even tell you why. And then the only way is to check this way, because that's what happened to me when I started in industry back in 1984. I had this wonderful solution with my finite element model. It was the first years that people were using Patran at the time. And my supervisor, a guy from England, looked at it and used the word that starts with the word bull and then 4 letters afterwards. And I was quite good as a student, as a master's student and undergraduate student. I had gone to a good university, so I was a bit upset and disappointed how he could just by looking say that the results were wrong. And he said, go do something and don't come back until you fix it. It took me a week and I had to go through a solution like this, which was approximate, but at least showed me, first, my boundary conditions on my finite element model were wrong. And second, the way I was applying the loads, I was presupposing the displacement pattern, which was not necessarily correct. Now, this guy was 20 years older than I am, and he could just tell by looking at it. So you have an option. Either you develop the intuition, and then you just do finite elements and use your intuition, or you develop enough understanding of the basic methods that you can use to check solutions like your finite elements. One of the methods is energy methods. We have 2 types of energy. In fact, we have a whole bunch of them, but the 2 of interest are the potential energy and the complementary energy. And basically, you can minimize either of them. Potential energy basically means you write your energy in terms of displacement. Complementary energy, you write it in terms of stresses or forces. And the theorems say, this is one way of stating them, say that in the first case, if you want to satisfy all the governing equations, you have to pick. Some of them you'll satisfy them exactly, and some of them you'll satisfy approximately. If you choose to satisfy approximately your strain compatibility, and strain compatibility means this equation here for a 2-dimensional problem. Remember, we said last time that if you eliminate the displacements, you can come up with a relationship that combines only the strains. So that is the equivalent of the strain displacement equations. So you can satisfy that exactly, which means you are making a displacement-based solution, which most finite element models actually do. And you can satisfy your geometric boundary conditions. That means any boundary conditions on displacements. You don't do anything about boundary conditions on the forces. Then you choose to satisfy your equilibrium equations approximately, which means you will minimize the energy. And if you minimize the energy, the result will, on the average or in an approximate way, satisfy your equilibrium equations. So, equilibrium equations, strain displacement equations, stress strain equations. Of those, I pick the strain displacement equations or the strain compatibility to be satisfied exactly. And then I will satisfy my equilibrium equations approximately if I minimize the energy. Now you might say, what happens to the stress and strain equations? They are still there. They just are a property of the material. They allow you relating stresses and strains. So as long as you use displacements to go to strains, and then eventually to stresses, you will use them and they will be satisfied. So don't worry as much about the stress-strain equations. The flip side of this is, okay, instead of satisfying the compatibility, strain compatibility, you choose to satisfy equilibrium. So first you satisfy stress equilibrium equations and all your boundary conditions for forces or moments, but you don't necessarily satisfy boundary conditions on displacements. It's not necessary. Then if you minimize the energy in terms of stresses, though, you will actually, on the average, satisfy the strain compatibility. Now, all this sounds like philosophy and relatively boring, but it's the basis of all good approximate methods we have. Finite elements are based on this. The methods we'll be talking here are based on this. And recognizing what you assume and what you satisfy is important, because sometimes you will get incompatible results and you don't know why. So if I summarize, the exact situation would say I have equilibrium equations, strain compatibility condition, which is the strain displacement equations with the displacements eliminated, the force boundary conditions, displacement boundary conditions. If I satisfy all these exactly, my energy is minimized. I don't even need to minimize it. It's minimized. The result I found minimizes the energy, and the solution is exact. Now I choose to invoke energy minimization here to eliminate one of these columns. So if I satisfy equilibrium equations approximately, that means I'm doing a displacement-based solution and I satisfy exactly my strain compatibility, I definitely need to impose the boundary conditions on displacements to be satisfied exactly. Minimizing the energy will do two things. Will satisfy approximately my equilibrium equations, and will satisfy my force boundary conditions on an average sense. That is, point by point, you might not get a force being zero at some location, but if you were to integrate at that location through the thickness, you would find that that integral is zero. The last option, the complementary energy, if you minimize the energy having satisfied your equilibrium, stress equilibrium exactly, you end up having satisfied strain compatibility approximately and the displacement boundary conditions approximately. And that would be, again, an approximate solution. Which of the two you use depends on what is easier, to assume something on the basis of displacements that you think represents the structure, or assume something on the basis of stresses. We'll be doing some stress-based minimizations in just a second, and also later on in the course.